Bagi Bayaw. Today I'm going to show how to solve a problem in heat transfer, chapter 11, combined conduction and convection heat transfer. So this is my problem. You can see this problem from the book of Unit A Single, page 188, problem 3-24. Consider a power transistor that dissipates 0.2 watt of power in an environment at 30 degrees Celsius. Transistor is 0.4 centimeter long and has a diameter of 0.5 centimeter, assuming heat to be transferred uniformly from all surface. Determine the amount of heat this resistor dissipates during 24-hour period in kilowatt per hour. The heat flux on the surface of the transistor in watt per square meter, and the surface temperature of the resistor for a combined convection radiation heat transfer coefficient of 8 watt per square meter degrees Celsius. So this is our figure. We're going to find the given. So our given, we have power transistor, which is 0.2 watt, and the time is 24 hour, and our convection heat transfer coefficients, which is radiation heat transfer coefficients, rather, 18 watt per square meter times Celsius, and our diameter is 0.005 meters. Since 0.5 centimeter, we're going to convert it into meters. So length is 0.004 meters, same with the diameter. We're going to convert the unit. So we're going to find first the amount of heat this transistor dissipates during a 24-hour period. So the equation that we're going to use is Q is equal to power transistor times change in time. So we have power transistor 0.2 watt of power in an environment times the time of 24 hours. So our heat this transistor dissipates is 4.8 watt per hour. Since the equation since the unit that required is kilowatt per hour, we're going to divide it by 1000. So our final answer is 0.0048 kilowatt per hour. Next, we're going to find the heat flux on the surface of the transistors. The equation for heat flux is equal to Q over area. So first, we're going to find the area surface. The equation that we're going to use is area of the surface is equal to 2 times pi times diameter squared over 4 plus pi times diameter times length. So we're going to put the given. So 2 times pi times diameter, which is 0.005 meter power of 2 over 4, plus pi times diameter 0.005 meter times the length, which is 0.004 meter. Our area of surface is 0.0001021 meters squared. Since we already find the surface, we're going to find the heat flux. The equation for heat flux is this, and we're going to input. So our power transistor, or the power in environment, is 0.2 watt over the area of surface is 0.001021 meters squared. Our heat flux is 1959 watt per meter squared. Then next, we're going to find the surface temperature of the transistor can be determined from the equation of heat power transistor is equal to convection heat transfer, or radiation heat transfer coefficients rather, times the area of surface times temperature surface minus temperature of the fluid sufficiently. So we're going to derive this equation to find the temperature surface. So this is the final equations. Temperature surface is equal to temperature of the fluid sufficiently times the heat transistor over the convection radiation heat transfer coefficient times the area of surface. So we have a heat power transistor from the environment, which is 0.2 watt, over our coefficient, which is 18 watt per meter squared, times the area of surface is 0.001021 meter squared. Our temperature surface is 193 degrees Celsius. Thank you for listening and have a great day, everyone.